Hi friends, Dr. Lewis here. Today we are going to be working on our expedition lesson. We're going to take it and try something a little bit different today. So what I want you to do is get something to write on and something to write with, because you are actually going to be taking some notes as you are working with me through this video. So what I want you to do is pause the video now, grab something to write on and something to write with, and when you come back, get ready to write. All right, friends, so we are going to be working on expedition in its true form. Expedition in class is combining reading, writing, and language arts with science or social studies. And so that's exactly what we're going to be doing today. We're going to combine reading skills with some science work. So let's start by reading our reading learning target for expedition. I can explain concepts in a scientific text based on specific information in the text. So what you're going to be doing is explaining a concept in a scientific text. Now, you're not just using your brain to do that. You're using specific information in the text. So it's kind of coming back to our previous work where we're using the text to answer questions, and in this case, explain science concepts, which is super cool. And this is reading informational 4th grade, and this is the 3rd standard. So this is a new one for us, kind of combining the first two. So again, we're going to be explaining concepts in a scientific text based on specific information in the text. All right, and now for our science standards. The guiding question that we're focusing on is, how do humans depend on Earth's resources? How do humans depend on Earth's resources? And we're going to try to answer that question by meeting this target. I can gather information to describe how energy and fuels come from natural resources and how their uses affect the environment. And here's the code for that standard. It's the 4th grade. ES stands for Earth Science. This S stands for Standard. And this is the 3rd Earth Science Standard, and it's the first chunk of that 3rd standard. So that's what that code means. 4th grade, Earth Science Standard 3, first one of those 3. Okay, so let's break this down. Today we're going to be gathering information. And how are we going to do it? We're going to read a scientific text. And what is the information going to help us figure out? It's going to help us figure out how energy and fuels come from natural resources. So we're going to be looking at energy and fuels and figuring out where they come from, what natural resources do they come from. And then a big part of that is how their uses affect the environment. So how do these energy and fuels that come from natural resources, how do they affect the environment? So that's what we're going to be working on today, friends. And the way that we're going to do that is we are going to read this book called Buried Sunlight by Molly Bang and Penny Chisholm. This book is about how fossil fuels have changed the earth. Okay, so before we get started on our text, we're going to read this text together. I want us to be prepared to answer some questions from the text. We're going to be explaining those concepts in this scientific text using specific information from the text. So our first question, and I do want you to write this down. Our first question is, what are fossil fuels? Now, you can Google this. You can think back into your brain of what you know about fossil fuels, but where should this answer come from? It should come from this text that we are reading, because that is the standard that we are focusing on. The standard isn't what do you know? The standard isn't what can you Google? The standard is I can explain concepts in a scientific text based on specific information in the text. So that is what I'm looking for. You are going to be answering this question in a Google form. And so it's really important that you have some notes so that you can take some notes while I'm reading the text. So make sure you write this down and you write down your answer as I'm reading, and you can transfer that into typing. So that's the first question. What are fossil fuels? So if you're taking notes, you'll probably want to skip a few lines, because if it were me, I would want to write my answer right here. And so the second question that we are going to answer is, how do humans use fossil fuels? So that is your second question that you are going to answer using the text. Please do not give me an answer from your brain or from your big sister or from Google. This answer should come from, that's right, it should come from the text. All right, so we've got one more question that we are going to answer using this text. So, how are fossil fuels affecting the environment? Now, this question, if you were to Google this question, you would get so many different answers. And that's why we're not using Google. That's why we're not using just our brains. That's why we're not using our people resources. We are using the text, my friends. We are using the text to answer that. And we're going to find all of those questions' answers in this text, Buried Sunlight. Okay, so again, the questions that you're answering are, what are fossil fuels? Getting it from the text. How do humans use fossil fuels? Again, getting it from the text. And how are fossil fuels affecting the environment? And that's right, you knew it already, you're getting it from the text. With these questions, the answers that we find from the text to these questions are going to help us answer our big question, how do humans depend on Earth's resources? And they're going to help us meet our target. I can gather information, which is what we're doing with this text. I can gather information to describe how energy and fuels come from natural resources and how their uses affect the environment. All right, so let's go ahead and get started with Buried Sunlight. So here's the insert right here. It says, what are fossil fuels and how did they come to exist? That's the big question. This engaging book explains how oil, coal, and gas are really buried sunlight trapped beneath the earth, beneath the surface of our planet for millions and millions of years. Now, in a very short time, we're digging them up and burning them, changing the carbon balance of our planet's air and water. What does this mean, and what should we do about it? Buried Sunlight, how fossil fuels have changed the earth. I am your sun, your golden star. Even from 93 million miles away, I warm your land, your seas, your air, and chase the darkness from your days. My energy gives light and life to your tiny earth. Yes, living things, including you, need energy to stay alive and grow. But you also use energy to heat your houses, to cook your food, to move your cars and trains and ocean ships, to run your computers and machines. Where does that energy come from? Most of it comes from coal and oil and gas, called fossil fuels. What makes them fossils? Like dinosaurs, they are ancient life that was buried deep underground. But fossil fuels are ancient plants. They captured light I shined on Earth millions of years ago. All this time, those fossil plants have kept my sunlight energy locked inside themselves. When you burn fossil fuels, you free the energy locked inside those ancient plants and turn it into heat and light. But how did those plants catch my sunlight energy and lock it into themselves? Through photosynthesis. Carbon chains, CO2, O2. This is what happens. Green plants everywhere catch my light and use it to pull in carbon dioxide, CO2, from the air. They use my sunlight energy to build chains of carbon, sugar, that form their leaves and stems and fruit. And as they photosynthesize, these same green plants release oxygen, O2, into the air you breathe. Phytoplankton. Well, what happens then? You gobble up the plants. You eat their carbon chains. You breathe in the oxygen the plant breathed out. You use it to break the chains and take their energy so you can move and live and grow. You breathe out the broken pieces of the chains as carbon dioxide, CO2. This is the cycle of life. This cycle of life is almost in perfect balance. All the plants together make a tiny bit more carbon chains than all the animals and bacteria eat. And the plants breathe out a tiny bit more oxygen than the animals and bacteria breathe in. The difference isn't much, but over millions and millions of years, a tiny bit each year can make a huge difference. In fact, these tiny differences gave you two of the Earth's greatest treasures, all the oxygen you breathe and fossil fuels. Here's what happened. Billions of years ago, long before dinosaurs roamed the earth, there was no life on land. There was no oxygen in the air. None. Back then, the only life on earth was tiny bacteria floating in the seas and tiny sea animals that ate them. Eventually, some of those tiny bacteria evolved into tiny green plants. They caught my light, made carbon sugar chains, and breathed oxygen out into the sea. Each year, they sent out a little more oxygen than the tiny animals could breathe in. So over millions and millions of years, the extra oxygen bubbled into the water and up until the water and air were rich with oxygen. Each year, the tiny plants made a few more carbon chains than the tiny sea animals could eat. So, over millions and millions of years, the extra carbon chains piled up on the ocean floor. Over millions and millions more years, bigger animals and plants evolved and moved onto land. And like the tiny plants in the sea, the land plants made more carbon chains than the animals and bacteria on land could eat. Each year, those uneaten carbon chains, dead plants, piled up. As even more millions and millions of years passed, all those dead plants with my energy locked inside were buried under layers of dirt on the land and on the bottom of the sea. Buried deeper and deeper, they were squashed and changed into coal, oil and coal and gas. Fossil fuels, my ancient buried sunlight. Those fossil fuels lay deep in the earth for millions of years as new and different creatures evolved. 150 million years ago, 60 million years ago, 15,000 years ago, 60 million years ago, 150 million years ago. Some plants and animals became extinct and more new ones evolved, but the cycle of life kept circling around. Eventually, just a few 100,000 years ago, you humans evolved and spread across the earth. You built fires to warm yourselves and cook your food, and one day you discovered fossil fuels, my buried sunlight. Very quickly, you began to burn those fossil fuels, the coal and oil and gas that took millions and millions of years for the cycle of life to make. Now, you use my ancient sunlight energy to power your world. When you burn the fossil fuels, you break their carbon chains, pull oxygen from the air, and send out carbon dioxide, CO2. Every year, as more fossil fuels are burned, more CO2 rises into Earth's air. Trees and plants and ocean waters pull in as much as they can, but it's not enough to keep CO2 from piling up in the sky. Your scientists are measuring it. They see CO2 is increasing faster and faster, and you humans are also cutting down forests and burning them to clear land for growing food, putting even more CO2 in the air. So what? Some people say. So this. CO2 is part of a blanket of gases around Earth. My sunlight passes through the blanket and heats Earth, but much of the heat bounces back into space. Certain gases like CO2 trap the heat and hold it. This helps control Earth's temperature. When these gases are lost from the blanket, Earth cools. When they increase in the blanket, Earth warms. Burning fossil fuels and burning your forests puts more CO2 into Earth's blanket every year. It traps more heat and warms the land and seas. Your Earth has begun to feel these changes. Some Arctic ice and glaciers are melting. The seas are warming, and some are beginning to creep over the land. The warming causes fiercer storms and droughts and floods. All around the Earth, weather is slightly different than it was in the recent past. In the future, the changes will likely be more severe. Some people still ask, so what? Earth has changed a lot over the billions of years since it was born. It's been much warmer and much colder than it is today. Why not burn the fossil fuels? Those people are partly right. I, your son, have watched your planet warm and cool many times. Earth has been so cold that ice covered beaches where you go swimming today. Earth has been so warm that palm trees once grew where snow falls now. Cold and warm, cold and warm. Your planet goes through these changes, and it always will, even without humans. But those changes happen very, very slowly over hundreds of thousands of years. The Earth's living creatures had time to adjust to the changing climate. But burning fossil fuels has poured huge quantities of CO2 into the air in just a few hundred years. This is very, 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 very fast. How many living creatures will be able to adjust to such rapid changes? How will it change the way you humans live? Billions of tons of fossil fuels, my sunlight energy, still lie locked deep inside the vaults of Earth. If you burn them up, Earth's CO2 blanket will grow thicker and thicker. Your Earth will warm so much it will change in ways that no one can predict for sure. But it will change. Will you humans keep burning more and more fossil fuels every year and risk the changes this will bring? Or will you work together to use my ancient sunlight more slowly, find other sources of energy, and invent ways to thin the blanket of CO2? The choice is yours. Notes about this book. Since the 19th century, human civilization has been run on ancient sunlight stored in fossil fuels. This is a book about fossil fuels, where they came from, and how using them has changed our species and our planet. Fossil fuel energy is sunlight energy captured by plants and phytoplankton and buried millions of years ago. The use of this ancient sunlight has shaped our modern world. When we humans started using fossil fuels, we did not understand that our actions could influence the entire planet. Now we know that they can have a profound impact on our Earth and its biosphere. We must consider carefully the impact our choices have on our current world as well as on future generations. Fossil fuels come from a natural global imbalance between photosynthesis and respiration. Nearly all life on Earth depends on plants for food. Animals, reptiles, insects, and microorganisms either eat plants or eat other organisms that have eaten plants. Plants make their own food through photosynthesis, using the sun's energy to link carbon atoms from carbon dioxide in the air into chains of sugar, simultaneously releasing oxygen. Carbon dioxide gas, or CO2, plus water, H2O, plus solar energy, photons, react and make sugar, C6H12O6, and oxygen gas, O2. Through photosynthesis, solar energy comes alive as the chemical bonds in sugar. To use that captured energy for themselves, animals burn the sugar during respiration, the reverse of photosynthesis. Oxygen is consumed, sugar is broken down, and carbon is released as CO2. Sugar, C6H12O6, plus oxygen gas, O2, react and make carbon dioxide gas, CO2, and water, H2O, plus released energy for biological work. This is what we call the cycle of life. Carbon and oxygen are constantly recycled, while energy flows from the sun into chemical bonds that hold the sun's energy. When we and other animals eat, our bodies break the bonds using oxygen and take their energy to do the biological work that keeps us alive. Each year, as they photosynthesize, all of Earth's plants and trees, seaweeds, and phytoplankton draw about 60 billion tons of carbon dioxide from the air as CO2 and build it into living biomass or living organic carbon. This is what feeds life on land and in the sea. If the global cycle of life were always in perfect balance, all the animals and bacteria would use all the oxygen that plants produce to burn all of the carbon chains that those same plants produce. But the cycle isn't in perfect balance. Usually there's a tiny bit more photosynthesis than respiration globally. This means that a tiny bit more organic carbon and a tiny bit more oxygen are produced than are consumed. On human time scales, say hundreds of years, these differences are negligible or not a big deal. Today, for example, there is only about 0.2% more photosynthesis than respiration. But over millions of years, in other words, geologic timescales, these tiny imbalances can accumulate and change the planet. In fact, they created the oxygen in our atmosphere that allowed the evolution of all complex life, including us. And they created the fossil fuels that make possible extraordinary human progress over the past 200 years. It took billions of years for life on Earth to fill the air with oxygen, and millions of years to make fossil fuels. Over the last 4.5 billion years, Earth has changed from a fiery ball of molten rock into our living home. At the beginning of Earth's existence, there was no life anywhere and no oxygen in the air. Then, around 3.8 billion years ago, primitive bacteria appeared in the oceans, and eventually some descendants of those bacteria began to photosynthesize, pouring oxygen into the seas and ultimately into the air. Larger algae and plants evolved, and over millions and millions of years, they flooded the air with oxygen. The oxygen-rich oceans and atmosphere shaped Earth and its diversity of life. The buildup of oxygen could only have happened if there was more photosynthesis than respiration over the vast stretches of time. Why didn't that plant matter get eaten? Because it became buried under layers of mud and rock and sand. And in some places, the carbon chains were slowly cooked by heat and pressure and converted to oil, coal, and gas. These are the sunlight savings bank of our Earth, fossil fuels. Humans like us first appeared in Africa about 160,000 years ago. By the end of the last ice age, 11,000 years ago, we had spread across the planet. For those early humans, the only energy available for food, shelter, and fire was the energy that the sun could provide over a typical human lifespan. Energy stored in materials such as wood. But when we discovered fossil fuels, we began to use this ancient stored sunlight to power our lives. Fossil fuels also ran our farm machinery and allowed us to make fertilizers, greatly increasing our ability to produce food. Our population grew and grew, consuming more and more fossil fuels with each generation. Burning fossil fuels has not only changed our lives, but it has also changed our atmosphere. It took hundreds of millions of years for the cycle of life to accumulate and bury Earth's fossil fuels. We've been digging them up and burning them for just hundreds of years. In other words, we have been using the sunlight energy in Earth's savings bank about 1 million times faster than the Earth is able to catch up and store new sunlight. And as we burn fossil fuels, breaking their carbon bonds to extract energy, we are pouring carbon dioxide into the atmosphere. Each year, the burning of fossil fuels and the vast forested regions releases roughly 9 billion tons of carbon as CO2 into the air. Ocean waters and plants and trees on land take up about half of that extra CO2. The other half is piling up in the atmosphere. In just a few hundred years, our human activities have caused a 40% increase in atmospheric CO2. That is faster than the Earth's atmosphere has ever changed before. And there are still trillions of tons of fossil fuels buried deep in the earth. If we dig them all up and burn them and continue to burn our forests, the carbon dioxide concentration in our atmosphere could be 4 to 5 times what it is today. Why should we be concerned about the rising CO2 in the atmosphere? The temperature of Earth depends on the amount of sunlight it receives, how much of that is reflected back into space, and the kinds and amounts of heat-trapping gases in its atmosphere. Those heat-trapping gases, called greenhouse gases, let sunlight through, but they trap its heat in their chemical bonds as it bounces off the Earth and radiates back towards space. The heat-trapping gases form a thermal blanket around the Earth. Without that blanket, Earth's average temperature would be 0 degrees Fahrenheit. In contrast, if our atmosphere had as much CO2 as Venus, our Earth would be too hot for life. The temperature of Venus is 867 degrees Fahrenheit. Other important greenhouse gases are water vapor, H2O, methane, CH4, nitrous oxide, N2O, and ozone, O3. Like carbon dioxide, atmospheric methane and nitrous oxide have been steadily increasing since the beginning of the industrial era. Molecule for molecule, they are much stronger greenhouse gases than CO2. So as they continue to increase, they will become more important in greenhouse warming. If we continue to burn fossil fuels, what will that mean for our lives? Since we began to burn fossil fuels and vast forests, the CO2 in our atmosphere has increased by 40%, and average temperatures around the world have increased 1.4 degrees Fahrenheit. Arctic temperatures have increased by twice this global average, and there has been a dramatic decrease in the sea ice of the Arctic Ocean. It will soon be ice-free. We cannot be sure that all of this warming is due to increased greenhouse gases, but mounting evidence indicates they play a significant role. Scientists predict that if we continue to burn fossil fuels, Earth's average surface temperatures will likely rise 4 to 10 degrees Fahrenheit by the end of the century. We can expect more melting glaciers and ice caps, and sea levels rising by as much as 3 feet. Climate in general will change. Droughts and floods will be more severe and storms more violent. As the oceans absorb much of the extra CO2, they will become more acid, dissolving corals and animals with shells, such as clams and oysters. Eventually, whole ecosystems will change with shifts in the type of plants and animals that can live in them. Geologists know the Earth has changed a lot in the past before humans even existed. How is this different? Indeed, throughout its 4.5 billion years, our Earth has been an ever-changing planet. After life appeared, it evolved with these changes. Recently, over the last 800,000 years, our planet has experienced regularly occurring ice ages with warm periods in between. Multiple factors cause these types of changes, including volcanic activity, the shifting of continents, and differences in the Earth's tilt and orbit around the sun. The response of the biosphere to these changes also plays a role, and all these factors influence climate and each other. So understanding the causes of past climate cycles is a huge challenge. Scientists have measured CO2 concentrations frozen in ancient ice to help us understand the relationship between atmospheric CO2 and past climate change, as well as how much the CO2 concentration has changed since humans began burning fossil fuels. Despite the complexities and uncertainties, we do know this. 1. The level of CO2 in the atmosphere have been increasing steadily over the past 100 years due to burning fossil fuels and deforestation. 2. CO2 is a heat-trapping gas. And 3. The Earth is warming. Given this knowledge, we have a choice. Do we continue to use fossil fuels at current rates and risk the consequences of a quickly warming planet? Or do we move as soon as possible to alternative forms of energy and conservation? So, what will we use for energy as we shift away from fossil fuels? No single energy source can replace fossil fuels. While there are many different technologies and approaches to collecting, storing, and distributing alternative energy sources, the fundamental non-fossil energy sources available to us are the following. Solar energy. We can collect the sun's energy directly through absorption into solar hot water panels or by photovoltaic cells. We can also collect it in fast-growing plants such as corn, grass, and sugarcane, and microscopic algae because they all photosynthesize and lock solar energy into their biomass as they grow. This biomass energy is like fossil fuel energy, but it doesn't take millions of years to generate. It is created and used in a short period of time, and thus it is renewable. It does not add any more CO2 to the atmosphere than it draws out. Energy from gravity. The ocean's tides are caused by gravitational forces between the Earth and the Moon, and the energy in tides can be captured for our use. Energy from gravity combined with solar. Gravity and the sun drive the global water cycle, evaporation, clouds, rain, and river flow, which can be captured as hydroelectric power. They also create the wind, which can be captured with wind turbines. Geothermal energy from the Earth's interior. The interior of the Earth is very hot. In certain places, that heat is carried near the surface of the Earth and can be captured and converted into heat and electricity. Nuclear energy. Radioactive elements like uranium can be used to generate heat, which can be a source of useful energy. Cost, safety, and waste disposal concerns surround nuclear power, making it a controversial energy source. Energy efficiency is important too. When we think about our current energy needs as well as those of future generations, we must think not only about the supply of energy, but also about how to reduce our demand for it. We will have to restructure our world, to design our houses, office buildings, factories, and all our vehicles to be much more energy efficient. And there are many things we can do right now to be more efficient. We can reduce unnecessary consumption of material things, all which use energy to produce. We can better insulate our buildings, use less heat in winter and less air conditioning in summer, and ride bicycles or use public transportation instead of driving cars, for example. But we will also need to apply all of our human ingenuity to inventing new ways to do things that require less energy. There are things we left out or greatly oversimplified in writing this book. Earth is an extraordinary planet, and its complexity is daunting. In our attempt to describe the essence of the fossil fuel story, we have left out or greatly oversimplified some very important processes that shape our planet. Here are a few pieces of the puzzle. The other part of the global carbon cycle, Besides what we call the cycle of life, carbon atoms are involved in a very important but very slow geological cycle that plays a role in regulating the CO2 concentrations in the atmosphere. When volcanoes erupt, they spew CO2 into the air. When it rains, some CO2 is washed out of the atmosphere and it flows into the sea. It is involved in a chemical weathering cycle that drives the formation and dissolution of carbon-containing limestone rocks. Unlike the cycle of life, it takes millions of years for a carbon atom to move through the geological part of the cycle. The Earth's interior. The sun is the narrator of our story, so we made it all-powerful. This shortchanges the enormous amounts of energy held inside Earth's core. Not only can this geothermal energy be captured for use by humans, but it also drives chemical reactions that feed whole ecosystems, such as those near deep sea volcanoes. The Earth's interior is an integral part of the Earth's energy system, but that is in another book. Bacteria and fungi. When we talk of the circle of life and represent living creatures that consume plant life, we have focused on animals, including humans. But bacteria, fungi, and other microscopic organisms are of critical importance in the cycle of life, breaking down plant matter that animals and insects have not eaten, and burning it as they respire. Collectively, bacteria and fungi consume oxygen and produce CO2 in vast quantities. Bacteria that live without oxygen. The last responders in the global feast on plant biomass are all the bacteria that live without oxygen. These anaerobic bacteria live wherever they can find a home away from oxygen, including inside our own bodies. Anaerobic bacteria play a crucial role in recycling elements required for life on Earth. Systems and feedback loops. One of the central features of our planet is that everything, life, water, air, soil, rocks, etc., is interconnected. It is a system. Systems have feedback loops among their parts. When one part changes, it influences what happens to another, and that influences another, and so on until the whole system has changed, often in unpredictable ways. Our planet, with all of its interconnected living and non-living parts, may be the most complex system imaginable. It took 4.5 billion years to become the place we think of as home. It is constantly changing. And because of the millions of feedback loops, its behavior is difficult to predict. Now that humans have discovered and tapped into Earth's energy savings bank, fossil fuels, we have become a dominant force in shaping the planet. We must do all we can to understand the potential consequences of our actions and act accordingly. The future of our species and that of most others will be determined by the choices we make. Okay, so what I want you to do for your second and third reads is I want you to have these questions available to you, and as you go back through this video and watch it again, I want you to write down the answers to these questions, and then you'll be able to answer them on the Google form so that I can see how you did. What are fossil fuels? How do humans use fossil fuels? How are fossil fuels affecting the environment? Good job, friends. Good luck.